And in the next session, uh, we have Professor Anjan Kundu sir. He is professor in Calcutta University. Uh, he will discuss about the Internet of Medical Things. He is the Associate Professor, Department of Radio Physics and Electronics, Calcutta University. Let me introduce you. It is our privilege to have Dr. Anjan Kundu sir. Sir, am I audible to you? Professor Dr. Anjan Kundu sir, am I audible to
Yes,
you?
I'm here. I'm here.
Okay, sir. Sir received his BTech, MTech, and PhD degree from Department of Radio Physics and Electronics, where he is currently serving as a professor. His research interest includes microwave tomography, bioelectromagnetics, medical antenna system design, RF biosensor design, RF in energy harvesting system design. Dr. Kundu has published numerous research papers in internationally acclaimed journals and presented his works in several prestigious international conferences. He also served as a reviewer of multiple IEEE journal, Terror Francis journal, and various international conferences. So I'd like to request Dr. Anjan Kundu sir to enlighten us about
Power
his
on.
topic,
Bluetooth mode.
Internet of Medical Things.
Device
Please,
paired.
please,
Okay,
sir, after you, sir.
just a minute. Am I audible?
Yes, sir, clearly audible.
Just my speaker. Okay, it is on now. So, very good afternoon to all the participants. I'm clearly audible to all.
Yes, sir, audible.
I'm just switching off the camera to increase the bandwidth actually. So,
Okay, sir.
uh, very good afternoon to all the participants, particularly RTS thanks to the organizing committee of this ATAL FDP, as well as on my behalf, RTS thanks to the organizer also for giving me an opportunity to share my knowledge, particularly my research areas, to all other faculties presented here. So as you all know, just let me share my slide first. This is the presentation. So the slide is visible to all?
Yes, sir, it is visible.
Okay, not in the presentation mode till now. So my topic is IOMT. Okay, so it's the term itself. It is not a new topic, rather than it's a worldwide and a new bottle light. So the term is new to all the researchers, particularly in the medical domain. But the technique or the technology or the concept behind IOMT is, I think, quite we are accustomed to that technology also. So as the participants here are from the different domain, I am not sure whether all are from technology or not. So far I know the faculties are from science domain also, science and technology, both mixing here. So there will be no technical discussion about IoT in my lecture. Otherwise, some of the guys will get bored in this lecture. So in this lecture, I will cover mainly the concept of IoT, how IoT works, how IoT serves to us, particularly to the society, and a bit of my contribution along with my team, not my contribution, rather than contribution of my team in this domain, particularly in the IoT. As you know, I am Anjan Kumar Kundu, and I am totally an RF guy. Means I am totally inclined to the bioelectromagnetics, rather totally inclined to the electromagnetics actually. So I am an antenna guy along with a bit concept of electromagnetics, and I have diverted my research but in a particular, rather than I focus my research to the bioelectromagnetics in a electromagnetics domain, means effect of the electromagnetics in biological bodies, that is bioelectromagnetics. So in my domain, not only the technical engineers or the technical researchers are involved, rather than lots of doctor friends. My doctor friends are also involved in this research, as because it is totally, whenever I'm talking about the bioelectromagnetics, definitely it is nothing but the interaction between the electromagnetics with the biological bodies. So definitely we have to know the biological bodies first. And for biological bodies, for understanding the biological bodies, definitely we need some medical practitioners in our research team. So my team not only consists of the researchers from the electronics or CSE, rather than it also includes some doctors also from the reputed institution in our state. So it's bit of biology, it's bit of technology. Technology means not only the electronics or electronics engineering, rather than it involves the computer science engineers also. We have to do a lots of codings. AIML, definitely AIML is a hot cake now, so quite natural it is. It has been included in a particular layer in IOMT. So that's what I will be going to talk in my coming lecture. In this lecture, how IoT works and how IoT involves with us in a various ways. That's why my topic in this lecture is not only IoT, rather than the technology transfer from lab to society. Whatever we are doing in research in our lab, how it can serve our society through IoT. That's the uh, main keyword in my lecture actually. Practically, how we can transfer the technology we are researching in our lab to the society or to serve the society. So let's start the lecture. I'm going to the presentation mode. So there will be no technical discussion. So don't bother about it. Just relax and have some views about a new technology. Not a new technology, whatever I've already mentioned that it's a old wine in a new bottle with some new added ingredients, actually, some particular ingredients so that we can term it as IOMT. So IoT is already known to us. It's a very common term to all of us, not only to the researchers, where it is very much common to the it is very much familiar to the common people also in our society. So IoT is nothing but a communication between different electronic devices through internet without any human intervention. So without any, that means it is an autonomous process. The communication between different electronic devices through internet in an autonomous process. That is the IoT. And there is a lots of example in IoT, real-time examples like the smart home devices. Means there will be a lots of sensors in the house which will detect different parameters in my house and act accordingly. So definitely we need some sensors as well as we need some actuators. Actuators will behave depending on the sensors. So it will be a predetermined procedure, how the actuators will work, like thermostat. If we want to measure the temperature of a room, there will be a temperature sensor like thermostat in the room. It will measure the temperature and accordingly it will control the AC or something like that. That AC is an actuator in this process. Similarly, for the farmers, it's a moisture sensor. It is widely used, particularly in the farming. So this is the basic IoT actually. I am telling you some basic examples of the IoT. Now, what is IoM? AIM term is being implemented within IoT. So IoT is nothing but the Internet of medical things. IoT is the Internet of things. IoMT is the Internet of medical things. IoMT means
Hello everybody, listen.
medical things. Now, what is Internet of medical? So basically, what is happening here? I am also a person of a IoT. IoT in IoT, what is happening? We are dealing with some data. That data has to be communicated between different devices in an autonomous way through internet. That is the key line or tagline of the IoT. But in this case, in IoT, that data will be a medical data. So the medical data has to be communicated between different medical devices along with the health practitioners through internet in an autonomous way. That is nothing but the IoT. So it's a type of the IoT technology, and the devices here will be used as a sensor or actuator, will be the medical devices, and they will communicate with each other along with the. I am also considering the health service providers, means the doctors, nurses, all such figures in the healthcare. They are also I'm talking, I am considering them as the actuators also. So basically all the devices will be a medical devices and they will communicate to each other. That means the data which is being transferred over internet will be a medical data. And the medical data, the difference between the medical data and the data, there is no such basic difference between the medical data, but medical and data in case of IoT. But in case of IoT, that medical data needs some security, add-on security. Okay, that's the basic difference when we'll be dealing with the medical data. In IoT, there will be a normal data which will be communicated or transferred between different devices autonomously. In case of IoT, that data will be medical data which needs some add-on protection. So here comes with the several research areas also. It includes different research areas also like AI, ML, cryptography. I will come later to that those topics in my later slides. So IoT is nothing but we have to deal with some medical data. We have to deal with some medical devices which will communicate with each other autonomously through internet. That's the basic concept of IoT. And I am a totally bioelectromagnetics guy. So my research area mainly includes a part of the IoT. I will come to the later, and there are some big contributions also in the field of IoT. So now we have an idea about the IoT. What is IoT? And some practical example which is already been implemented in IoT or implementing IoT. One is the RPM. RPM means the remote patient monitoring. That means IoT comes in the scenario, but just during the COVID. The earlier the IoT is in the dormant mode, but to 2019, it's 2019 onwards, IoT is playing a serious role, particularly in the healthcare services. So one of the most popular example of IoT is the RPM. That means the remote patient monitoring. Means the health condition of that patient can be monitored remotely from the hospital or from the doctor's end. The person don't need to visit the clinic in person or visit his medical practitioner in person. It's mainly important for the chronic diseases or the long-term diseases. I will give some examples later. Then comes one of the popular example of IoT is to track the patient's medication, which medicine he or she is taking, and how frequently he or she is taking that medicine. That patient is taking that medicine, so we can track the patient medication orders. We can track the location of the patients admitted to hospitals. It is quite familiar to all the hospitals in our locality or in our state. So there is a tag which is known as the RFID. I will come later. Those are the practical the biosensors. So we will put a tag on the patient to track the location of the patients admitted to hospital. Also, the fourth point, it's a very important to me because I am doing my research in this point, particularly in this domain, collecting data from the patient's wearable mobile health devices. I'm not explaining right now at this point. I will come into details in this point in my later slides. So we have to this point particularly deals with collecting some data from the patient. That means we are not from the patient, rather than the patient's wearable devices. Means the patient has to wear something, that is the wearable devices that will collect the patient's data, means medical parameters. Then it will be transmitted to the server or to the medical practitioner directly to his mobile, to his or her mobile through IoT. So this domain, collecting data from the patient's wearable mobile health devices, basically deals with that domain of the IoT, and I will come into the details of that point because my present research domain is one of my present research domain is these wearable devices, actually to develop the wearable medical devices to collect the data for the IoT. Also, there is a facility that can be implemented through IoT, but I think it is not being implemented in our locality. That is connecting the ambulances to the medical facility. Whenever the ambulance is carrying the patient, that patient's parameter along with the ambulance location will be conferred to the nearby hospital to which the ambulance is going to visit. So we can track the ambulance as well as we can track the patient's parameter who is residing or who is within that ambulance. So these are the basic key terms related with the IOMT. One is the electronic health records, means the data that has to be collected from the patient, means the medical parameters. Telehealth, we are already aware of the telemedicine or telehealth. We can through online, there are lots of portals on the online right now through which we can discuss our difficulties or our diseases with some remote doctors or remote medical practitioners. So that is the telehealth. Now comes the third point is the wearable devices. I will explain in details. Then comes the mobile health apps. Lots of apps are there. If it is being downloaded either in the patient end or in the doctor end, so that they will communicate to each other with that mobile health apps. Then comes the personalized medicine. I have already mentioned in the earlier slide that we can track the patient's medication records. So that is the personalized medicine. Along with point 6 is the telemedicine. It is already being popular to us. Then comes the electronic medical records. Number one is the electronic health records. It is at the patient end, and electronic medical records (EMRs) is in the hospital end, means service provider ends. So these are the basic keywords which are related to the IOM, and almost each keyword deals with a new research domain. I will try to give you an idea about some new domains over which the researchers definitely the academicians are working or doing research on those domains and may inspire some of you to pursue his or her research work in that domain also. So these are the basic keywords. I will explain it later, particularly in the third point, that the wearable devices. So now we can have an idea of what IOMT is and how IOMT works, or rather than what are the keywords which are associated with IOMT. So we need the medical devices, we need the Wi-Fi connection, and we need some communication protocol. Definitely communication engineers are also involved in this IOMT research work. We need electronics engineers who specialized in communication. And so we need medical devices, we need Wi-Fi enabled medical devices through which that IOMT data, we have to collect some data through the biosensors. That is, I will be coming to the architecture also. So we need some sensors, we need a communication channel, we need some service providers, and they will be connected through internet or Wi-Fi. And we can talk also about the cloud platforms also that will be required when we have to, or the medical practitioners want to analyze the data. Then only we need the cloud platforms. Otherwise, the communication will be on spot. Means just we need a Wi-Fi connection. If we want to store the data, to analyze the data, then we need a cloud platform. And if we want to communication on spot, means real-time communication, there will be no storing of data. That in that case, IOMT, for that IOMT, we need only Wi-Fi connection. So this is the basic system architecture of an IOMT. The leftmost block is the data collection center. So there will be in the data collection center, this is my domain actually. The data collection center is my domain of the research. So here we need some healthcare sensors which will collect the data. The healthcare sensors will be of different types. I will be coming into the details in my later slides. So maybe it can handle device. It will be connected to the server. So the data is being collected. Now comes the data management layer. In the data collection center, the researchers with electronics background, electrical background, I think these two domains are very much related to the data collection center, particularly to designing those biosensors. The second block of this architecture is the data management layer. Data has been collected from the sensors. Now the data will be stored over the cloud for the further analysis for the medical practitioners. So in this data management layer, it will attract, particularly, I've already mentioned there will be some key words associated with IoT, which makes it distinct from the IoT. And number one is the protection. So definitely cryptography plays a vital role, is to play a vital role in the data management layer. Whenever I am whenever a medical data is being transformed from the source to destination, means from a sensor end to the medical practitioner end, it has to be encrypted in a particular way to keep it secure. Security is the main factor of the medical data. So cryptography is it can be a popular research work, particularly in the data management layer of the IoT. Not only cryptography, also whenever we are a term has been mentioned here, distributed computing, data storage is the DAS, data acquisition system, cloud computing and distributed computing. I will mention in my later slides that there is a data collection complexity, means that the data which is being stored in the data management layer is not a data of a single variation, rather than lots of variations will be there in the data collection. So it has to be differentiated and has to be sent to the through a proper channel to the proper practitioner. So in this case, AIML recently is playing a pivot role, particularly in the data collection center and data management center. So AIML and cryptography are the new thrust areas, particularly in the data management layer of the IoMT. Now comes the last one, that means the end product, that the medical server layer. Mainly it belongs to doctors or nurses, mainly to the medical practitioners or to the hospitals. So it is basically nothing but some instruments which will be residing within the hospital, which will provide precaution or proper steps to be taken in case of any medical urgencies to that patient. Also, it will be communicated to the doctor so that the doctor can prescribe something directly to the patient. So this section leads to the medical server layer. So these are the basic three blocks in the IoMT system architecture. One in the data collection sector, mainly deals with the biosensors, different types of biosensors, and me along are working on these biosensors in the RF biosensors rather than. Now comes the data management layer. Mainly computer science guys deals with the data management layer, having interest in cryptography or in the IML, integrated data management and data analysis. And the last one is related to the hospital. So these are the possible benefits of the IoMT. The first point I've already mentioned, that the patient monitoring system, that means there will be a round the clock health monitoring of the patients, particularly with the long-term diseases or the chronic conditions. Second is the accessibility, means the patients can have more access to the health service. This is the accessibility, particularly to the patients. Third one is the cost control. Cost control in that sense, the patient doesn't have to visit the healthcare facility in person. So for natural, the cost, a portion of the cost can be decreased. Along also, the doctors not necessarily need to visit the patients in person. So in an overall term, there will be a reducing clinical cost. The term is the clinical cost. Cost control means there will be a reducing clinical cost, not only from the patient side, rather than in the whole, there will be a cost reduction in the entire healthcare system. Now comes the one of the possible benefit is the improved patient experience. Quite natural, the patient will be accustomed to the new technology, and which will facilitate the patient for the self-service. We don't no more depends on the doctors always. Along on the basis of the analysis of the data, we can take some decisions also. So this is the self-service, and also it minimize the in-person visits to the medical centers. Consumer grade variables, I will come later to these points. And now comes the accuracy. It's a vital point in case of IoMTS, because I've already mentioned that if we need the data to be analyzed, it has to be stored. So we need a cloud platform. And accuracy means there will be an accurate insights into the health condition of the patients. I'm just giving an example. It has been already been written here. I'm just reading it out. That an IoMT enabled blood pressure monitor can provide several days of blood pressure and heart rate readings that yield a more accurate diagnosis than the data from a single doctor's read. Just explain it again. And if it is an IOMT enabled blood pressure monitoring system, then it will monitor my blood pressure, and rather than it will collect the data of my blood pressure and heart readings in a continual way or in a sequential. So at the data end, there will be lots of data of my blood pressure along with my heart rate. So whenever I am going to a doctor, the doctor will measure my blood pressure or the heart rate for a single time. So there will be a single data that will be available to the doctor, and depending on that single data, the doctor has to take the decision. But if I have a IOMT enabled blood pressure monitor along with the heart rate monitor, so at the doctor's end, there will be a lots of data over which means depending on those lots of data, the doctor can be able to take more accurate decision or can have a more accurate diagnosis. So that's a major benefit of IMT, particularly for the patients with chronic conditions or long-term diseases. Of course, there will be some challenges of IMT. First one is the implementation. Definitely, we have to develop a device that will be compliant with the industry standards. It is very much complicated whenever we are going to develop a healthcare devices. Lots of factors will be coming in. Ethics is the most vital factor here. Human ethics. We can't test any biological sensor on a human body without going through the ethics committee of the concerned institution. So definitely it's a very tough to define or to rather than to develop a device which is compliable to the industry standards. Second is the upfront cost. Definitely the initial implementation of the IoT technology is very high. The cost of the implementation of the IoT technology is very high. So we have to definitely it will take some time to have some profit after the implementation of the IoT technology. That means we have to wait a few more years after the implementation of the IoT technology to have profit, means to have a positive return. Security, I have already mentioned in the data management layer. Security is a key factor whenever you are dealing with the medical data. That data anyone can breach that data. Attackers can use that stolen data to obtain medical services. It's a very common practice here. So definitely we need some security, which is a challenge in case of transferring the medical data through IoT. That's why cryptography rules in. Here cryptography plays a pivot role whenever you are transferring a medical data from the sensor to the server or to the doctor. Now comes the data ownership. It is also very complex in nature. That's because whenever the IoT data is collected, the patient can use it, the software provider can use it, and also the other healthcare persons are also can use it or can access that data. So depending on the context, the data rights for each party can be complex. Data belongs to whom? To the patient. That's because it has been collected from the patient. So apparently the data belongs to patient, but the service provider is transferring that data from the patient to the doctor. So that service provider is also accessing the data. Also, the healthcare providers are taking decisions or suggesting some medicines or medical treatment to the patient depending on those data. So everyone is accessing those data. So there arises a problem of the data ownership, means to whom the data belongs, to which party the data belongs. That's a challenge in the IoT also. That is not there is no such government rules in our country, particularly in case of IoT. So data ownership is still a challenge in case of IoT implementation. Now comes the data classifications. I've also mentioned that term data classification in data management layer also. So I'm giving an example particularly for the data classification. Suppose I've already mentioned the point that we can track the location of the patient when the patient is getting admitted in a hospital. So we can track the patient location. That is not a medical data. Okay. But the data collection or the parameters which are being sensed from that patient, are medical data. So all the data will be transmitted in a sequential pattern. So quite natural, monitoring a user's location is a non-medical data. But that data can be used to track a spread of infectious disease. If I am carrying a, particularly it becomes more popular after COVID. So if I have a sensor in my body which will track my location, it also tracks the spread of the infectious disease which I'm carrying. So that data is a medical data, that the spread of the infectious disease. That is a medical data, but it has been merged with a data that is the location of mine, means the location of the patient carrying that infectious. So there is a lots of challenges in the data classifications. A large volume, the data is not a smaller volume. The IMT data is very large. So quite natural, there is a challenge in the data classifications of the non-medical data and the medical data. So AI as well as the ML recently they are rolling in particularly in this data classification domain of that data management domain of IoT infrastructure or IoT architecture. And one of the challenges is the user experience. Hello. Any problem in case of, in my hello?
Yes, sir. Yes, sir. I have muted him. Yes,
Okay,
sir. Please
am I
go
audible?
on.
Everyone
Yes, sir.
can,
You are audible. Audible, sir.
okay. So user experiences, I am also facing this challenge as because I am dealing with the biosensor. Suppose I am wearing a jacket, carrying all the biosensors which are sensing my blood pressure, my heart rate, my glucose, along with my temperature, etc. etc. So whenever I am wearing the jacket, it's a wearable devices. I will come later. So whenever I am wearing a devices, whenever I am wearing a medical devices, medical sensor device jacket, quite natural, I need to know how to handle that jacket. I can't wear it off in a irregular manner, otherwise the sensor will get damaged. So user experience is a great challenge whenever we are using in-body sensor or on-body sensor or wearable sensors on the patient. That is so the designing medical devices. Definitely, we have to take care of the medical devices so that it can be weared out by handling minimum mishandling of the patient. Along with, we have to train the patients also to use those wearable devices. So that's a great challenge in case of implementation of the IOMT. So these are the different types of IOMT devices. One is the in-home IOMT, means the IOMT devices will be around the patients. One is the personal emergency responsive systems. For example, particularly for there is a fall alarm which has already been implemented in the healthcare systems. Suppose elderly person, they have a tendency to fall due to their age. So whenever that patient fall, an alarm will raise at the nearest medical center that this patient has fallen. We need ambulance or we need personal health care. So that is a fall sensor. So that is the personal emergency response system. That fall sensor are already been developed and already been implemented in the health system also. So this device, particularly this personal under this personal emergency response system, the device alerts a hospital when a patient experiences an emergency. This is one of the example of the in-home IOM. Another one is the RPM devices. RPM, we have already known that term, that RPM means remote patient monitoring. So RPM devices contains a lots of sensors which will collect the medical data in a continuous way or in a sequential way. And the data will be either transferred to the medical practitioner in real time or it will be stored in the cloud for further analysis by the practitioner in the later situation. So these are the possible or the some of the popular examples of the in-home IoT. Wearable IoT. This is also known as the on-body IoT. Presently, my team are working on this wearable IoT actually, or on-body IoT. It's a very complex in nature, as because it has to be weared by the patient. So we need to train the patient. I already mentioned that the last point, user experience. User experience is a very challenging factor in the IoT, particularly for those wearable devices. So wearable IoT means on-body IoT. That means some sensors has to be connected with the body, on the patient's body, and that sensor will record the information. Then, in a similar way, it will be transferred to the doctor, or it has to be stored in the cloud. So there are two types of wearable IoT rather than two types of wearable. One is the consumer grade of wearable, means the patient do not require any medical supervision whenever he or she is using these wearable devices. And the other one is the medical grade wearable, means the patient needs the medical supervision, means he or she needs the supervision of a doctor whenever they are using, that patient is using a medical grade wearable. For example, I'm just giving an example here. There is a neuromodulation device. It is already in the market, and it can manipulate the patient's nervous system to mitigate the pain. To reduce the pain, it will manipulate the patient's nervous system. It is a neuromodulation device. It is already in the market. So definitely, whenever we are using a neuromodulation devices, we need the supervision of a doctor. Otherwise, the smart pill. I will come later to the smart pill, particularly, or the ingestible sensor. This is actually the ingestible sensor. It is just like a capsule. We have to swallow it, and it will do some miracles within our body. That is particularly the capsule endoscopy. I will come in later in my later slides, particularly the smart pills. It is also a medical grade wearables, and we need the supervision of a doctor whenever we are using the smart pills, just like the neuromodulation devices. Mobile IoT, it is already in the market, commercially available, means the IoT devices will be interfaced with the mobile or the BLE, Bluetooth enabled devices. Just like a RFID tag. I have just shown a picture here in the slide. This patch actually is a continuous glucose monitoring patch. It will be inserted within your skin of 1 mm. It will be inserted. A pin will be the pin actually. This pin will be inserted to your hand at a depth of 1 mm, and it will sense your glucose monitoring in a continuous way. And whenever you put your mobile close to that sensor, it will get your reading. Just giving an example here. It will have your glucose monitoring reading on that mobile. Definitely, there will be an app in that mobile. Through that app, the mobile will access the data of that sensor and will display on your screen. It is already been available, but this we have to replace these sensors at a regular interval of 2 or 3, 4 days. We have to buy a lots of sensors. It is known as the. I am working on glucose monitoring system actually, so I know these sensors in details. So there is a chance of infection also, as because it's a minimal invasive devices. Minimum invasive devices for glucose monitoring. The technical term is something like that. So I will be coming in later to this glucose sensor actually. So mobile IoT, it is already been popular in case of IoT. The cell phone has to be connected through some app with those medical sensors. I am giving an example here that the glucose monitoring system, which can be that data can be seen by the patient himself or herself in his or her mobile through an app. And definitely we have to use this type of sensors on our skin. So definitely it is very effective. Now comes the public IoT. Public IoT means the IoT devices will be dispersed throughout a geographic area. Means point to point, just for example, point to point care kiosk. If there is the health center is not within a reach of that patient, so in the remote areas we can create a point to point care kiosk where the patient will visit that point to point care kiosk, will submit the data, and it will be analyzed by the doctors which is being present remotely. Okay, so doctors will be not in the point of care. There will be some devices. The data will be entered by the patient, and that data will be collected and will be sent through IMT either in real time or through cloud to the medical practitioner, just like a robotic surgeon. A crude example, point to point care. And also the environmental health sensors. That it is particularly related to the air quality networks actually, the environmental health sensors. So there will be some sensors in the environment which will monitor some environmental parameters continuously. Which parameters? Now those parameters which will affect the public health, like the air quality or humidity So air quality is a popular example. Can see some air quality sensors along our roads and along the sideways of our roads. Even in Calcutta also we have air quality sensors in the bypass. It will, there is a large display and it will show the numerical figure mentioning the air quality at that region. So that is the environmental health sensors, and that data can also be sent through IoT to the nearby hospital so that they can have a track of those patients suffering from that poor or good air quality. Now comes probably it is the last one of the types of the IoT devices, that is the in-hospital IoT devices. Means these instruments will be decided within the hospitals. It will be not accessible by the patients, rather than it has to be accessible by the medical practitioners, like the infusion pumps. They have, whenever a patient get admitted in any nursing home, you will see that there will be a display and lots of sensors which will be connected to the patient body, not only on the body but also on the fingers, clip-on type devices on the fingers, and lots of parameters will be displayed on that dashboard. That is nothing but an infusion pump. It will sense your blood sugar level, it will sense your oxygen and all other temperature, all other parameters, heartbeat, and it will be displayed in a continuous way in that dashboard. That is known as the infusion pump actually. So it is a in-hospital IoT. Also on the RFID tag. RFID tag means radio frequency identification. So basically it's nothing but a tag which will be connected, which will be placed on your skin. And through that RFID tag, the patient will be connected to the entire healthcare system, its location along with all other parameters. So those are the RFID tags. It is also a popular research area, particularly in the for the RF persons, radio frequency persons, to develop such tags. So these are the earlier slides. Basically covers the basic knowledge to acquire a basic knowledge of IoT. What is IoT? How IoT works? What is the basic architecture of an IoT? I didn't. So I've tried to cover all those basic concepts with my earlier slides. Now comes, if we can recall, I'm going to the slide actually, that slide. If we recall that there are three layers. One is the data collection layer, one is the data management layer, and the other layer is the medical server layer. Data collection layer mainly deals with the sensors which has to be placed on the patient's body. And presently I am working in this data collection layer of that IoT. So my next slide, it has been mentioned as the medical electronics actually. IoT is a part of medical electronics. So here I will discuss some key words which is related to medical electronics as well as related to that first data collection layer of the IoT architecture. These are the key words actually. I will discuss these terms one by one. One is the body area network, also mentioned as the WBAN. If it being placed, that body area network is being placed wirelessly, then it will be a WBAN. If it is that network is sensor based, then it will be known as BSN, means the body sensor network. And BAN and WBAN, if the sensor network is medical electronics related, then it will be more specifically known as MBAN, or the medical body area network. I will come in my later slides to have an explanation of those terms BAN, WBAN, BSN, all such things. Now comes the biomedical telemetry. It is the hardcore IoT, means the transmission of the data, how the biomedical data is being getting transmitted through a channel. It's basically a communication. So there will be no technical discussion in this biomedical telemetry particularly. It totally based on communication engineers. So the communication engineers deals with the biomedical telemetry of that medical electronics or IoT domain, basically to transfer the data, to collect the data, and to transfer it to the destination or to store in the cloud. Then BCI or BMI, brain machine interfacing or brain computer interfacing, is a very, very hot topic now, particularly in the research domain. But it is not limited to only to the computer science engineers, rather than mechanical engineer, electronics engineer, lots of science, lots of physics, chemistry, all are related with this brain machine interfacing. A chemistry guy can also do the research in this brain machine interface. or BCI. I will give you some examples of BCI. Then comes the microtomography. Tomography, actually, microtomography was my PhD. Whenever I was doing PhD, my PhD topic was the microtomography. Actually, I will give you an idea what can be done, how can be a biosensor can be developed through microtomography. Tomography means actually imaging, not image processing. You have to create an image through microwave of a particular cross section of a human body. That is known as the microtomography. I will discuss in details later. And another topic, also my research area also, is the RF energy harvesting. Means it is also known as the sustainable energy. Means we have to harvest energy from the RF signals. In a crude way, we can say I can collect 900 millivolt from air. From air, I can develop a 900 millivolt. I've already developed that actually. 900 millivolt, very less power, very less voltage rather than, but energy can be harvested from the RF signals, which are ambient, which are abundant in our air, in our surroundings. It is particularly required to power the sensors, to power the medical sensors, which will be placed over the body, over the patient's body. So we need power for the sensors to collect the data. So instead of using battery, we can have the energy from the air itself. So that topic, that is also an hot topic. Lots of research are going on, particularly on that RF energy harvesting. So these are the keywords I'm going to explain in my later slides. I will try to explain it in a qualitative way without going into any technical details. Wireless body area network, the term was first coined in 2001. So WBAN mainly relates with these three terms: on body, in body, and off body. These are the practically, depending on the position of the sensors on a patient's body, the WBAN can be generally deals with on body, in body, or off body, and or all the three can be present. Either any one or any two can be present within the WBAN. So on body and or in body and or off body ultimately constitutes the WBAN. So on body means communication within on body networks and wearable systems. So definitely in case of on body IoMT, the sensor has to be placed on the body. In body means there will be a communication between the medical implants and sensor network. Medical implants means we have to, the patients need a minor surgery. The sensor has to be placed within the body. That is known as implant actually. So we have to implant the sensor within the body, and then that sensor will communicate with the external world. That is the in-body communication or in-body ION or in-body WBAN. And off-body means there will be a communication between off-body means there will be no physical connection between that sensor and the human body. There will be a minimum air gap. For example, if we wear a jacket over our shirt, so definitely, or over our t-shirts, so definitely there will be no physical connection between the body skin and that off body sensors, that those medical sensors. That is known as actually that deals with the wearable sensors. Actually, those sensors are known as the wearable sensors. So that is the off body communication or off body IoT or off body WBAN. These terms are totally medical terms, not medical terms, medical electronic terms actually. So I'm trying to explain the on body through some pictorial representations. Particularly for the sports person, we need the on body WBAN or on body IoT. Lots of sensors are placed over a sports person. They used to collect the vital parameters of that sports person, and then that collected data will be sent through this unit. This unit is known as the body one base unit. All the sensors are connected to body one base unit, and this body one base unit will send the data wirelessly to the desired destination, either to the cloud or to the doctor or to the observer who is observing this sports person. So this is a practical example of the WBAN, particularly on body WBAN or on body IoMT. Names comes the in body. I will come into details in the in body. My team had did some work in this in body actually. So practically we have to implant the sensors within the body. That sensor can measure your heartbeat. That sensor can monitor your glucose and all other vital parameters. Then those data which is being sensed from your body will be sent out of your body to connection to communicate with the external world. So lots of complexity are there, particularly for the in-body communication or in-body IMC, but we have to deal with the implanted devices here. So lots of factors are there whenever we are going to implant sensor within a body. So lots of complexity are there. I will come later with those complexities actually, as because I did some work in this domain, so I know the complexities. Now the off-body. Off-body means, off-body WBAN means the communication in case of on-body. Where is the on-body? This is the on-body. So we have a body-worn base unit which is collecting the data from the on-body sensors. Now this body-worn base unit will communicate with the external world. That communication is known as the off-body communication or off-body IOM. Again, I am just trying to explain it again. In case of on-body WBAN, means there will be a network on the body of the patient. Means lots of sensors, numerous of sensors will be placed on the body of the sports person here, for example, and those sensors will be connected to the body-worn base unit. Okay. So this is the on-body communication between the body-worn base unit and on-body sensors. Now the data collected by the body-worn base unit has to be communicated to the external world. Means either it has to be stored in the cloud, or it will be it can be directly sent to the observer of that sports person. That communication is known as the off-body communication. So this is the sensors. Might be a patient or might be a sports person. There will be a base unit. Now the communication between these base unit with the surrounding networks is known as the off-body communication or off-body IOMT or off-body WBAN. In case of military also, we can use that off-body communication or off-body IOMT. It's a common practice right now in our army that we can monitor the vital parameters of a soldier who is in the war front. Whenever the soldier in the battlefield, we can remotely monitor the vital parameters of that soldier, and we can calculate the stress factor of that soldier, and depending on that stress factor, we can command that soldier to come out of the battlefield or to retreat from the battlefield. That we can do. That is already available in our defense actually. So we can remotely monitor the health parameters of a soldier who is in the battlefield, and depending on its stress factor, we can order or command the soldier to retreat or come to the base. That can be done. It is totally off-body communication. So these are the some practical examples of the different types of WBAN. I'm telling about all the wirelessly. Now comes the implanted or ingested RF, that in-body communication. Just give me a moment. What happened? Okay. So the most popular example, okay, I am just going through the entire slide so that it will not be. So I think this is the entire slide. So one of the popular example of the implanted devices, not ingested, implanted devices is the pacemaker. This is a real-time picture of an pacemaker. It is a single lead and it is a pacemaker. Now we have to buy pacemakers for doing some research work, particularly for the implanted device. I've already bought a pacemaker. So pacemaker is the one of the most popular example of an implanted devices, and also the AICD. AICD is very less known to the patients. It is an automatic implantable cardioverter defibrillator. Means we have to implant sensors within the patient. There will be a data acquisition system on your body. That implants will collect all the vital parameters of your body and will be the data will be collected with the DAS, data acquisition system. One popular research work, particularly for the implanted, is the bionic eye. I will come in details with this bionic eye. Bionic eye means an artificial eye. Though the person who can't see through his normal eyes, normal biological eyes, we can replace that eye by an bionic eye. How a bionic eye works and what are the research works are going on, I will show you all in my latest slides actually. So it's nothing but an artificial eye. This is the first prototype picture of the bionic eye. It has already been developed. It has already been developed. This bionic eye has already been developed in its prototype stage. Next thing is the cochlear implant. Cochlear implant means the person who can't hear, that person can hear actually by these artificial devices known as the cochlear implant. It is not an hearing aid. Rather than it needs an implantable devices and with some transmitter and receiver, and there will be a wireless communication with your audio nerve in your brain. That is the basic principle of the cochlear implant. I will come in details that cochlear implant. And this is the ingestible devices. Wireless capsule endoscopy is the ingestible devices. Lots of research work are going on this capsule endoscopy, actually wireless capsules. My team is also working and is also working on this wearable capsule endoscopy. So it has already been developed by USA by a company named Pilcare. It is nothing but a capsule. I will come in details about the internal structure of this capsule. You will be surprised to see all those miniature electronics are within this capsule. Nothing but is an electronic devices. This Pilcare is nothing but electronic devices containing camera, LEDs, data acquisition system, antenna, all such things within this capsule. So I will explain it later. This capsule is right now around 30,000 for a single capsule. It cost around 30,000 for this Pilcare. So this is the biotelemetry. I've already mentioned these are the implantable antenna, power supply, biosensor. So those will be placed on the human body. There will be a kind of communicating channel, that means the IoMT. If we need a cloud, then we can use the cloud here within the channel. And this data has to be connected with the base station. So this is basically the pictorial representation of the entire biomedical telemetry. How much time I have? 6:15. Okay, my time is up to 6:30, I think. Sudipto?
Yes, sir. It is 6:30, but as
Only
your
50.
session has started little late,
Actually,
you can continue more.
I have lots of videos which can show you how how the world is working in real time. Okay, so I'm not
Yes,
going
sir, you
into
can
the.
continue after 6:30 also.
Okay, let's see. I have almost more than 100 slides. Okay. So I am just speeding up. There is a term known as SAR. Everyone know the SAR actually. Everyone is aware of the SAR, but we are not showing. We are not actually want to show it. If we have a back of your mobile, if you can see the back of a mobile, this is the picture of the back of my mobile. And there is a term is the SAR. If you can see, it is a limit of 1.6 watt per kg. And the SAR of this mobile on your head and on your body is 0.506 and 0.833. Every mobile has this sticker at the back of the mobile. Every mobile has this sticker at the back. Otherwise, this mobile can't be available commercially in the market. So what is SAR? It is a vital, challenging parameter, particularly for the implanted devices actually. So specific absorption rate is nothing but whenever we're using our mobile for a prolonged time, actually there is a communication between your audio nerve and the mobile. That's why you can hear the mobile sound through your ear. So there will be a continuous energy exchange between your brain and the mobile. And I think we all are aware whenever we are using a mobile, the portion surrounding our ear over the head is getting heated. It is practical. That's why it is getting heated, as because there is a continuous energy exchange between the mobile signal and the audio nerve within our brain. So this is the basic figure actually. The mobile is receiving the signal. It is transmitting the signal in all directions, also towards head also. That's why we can hear through our audio nerve.
So how much energy is being exchanged between what is the permissible range of that energy so that our brain will not get damaged? That is limited by SAR. So in India, SAR 1 gram limit 1.6 watt per kg means maximum 1.6 watt per kg can be exchanged in India through a mobile. So every mobile has to obey this limit. If it crosses beyond that limit, that mobile will be banned by the Indian Telecommunication ITC. That's why every mobile carries a sticker at its back mentioning the SAR limit. And whenever we are trying to develop a biosensor, particularly on-body or in-body biosensor, definitely we have to calculate the SAR of that sensor and have to design that sensor accordingly so that it obeys this 1 gram limit. It is the 2 gram limit also. For practical products, for research, this is the 2 gram limit, and for practical products, it is the 1 gram limit. There are two limitations actually for SAR in India. Not only in India, there are limitations over the world. These figures depicts only for the India actually. So there will be a continuous exchange of energy between the mobile and your contact area of your body. So quite natural that portion of the body will get heated, and that this SAR limits that energy exchange to ensure the safety of that portion of your body. Whenever we are placing our mobile close to the ear, definitely the surrounding region of the brain, surrounding region surrounding the ear, the region surrounding the ear of the brain, definitely it's get heated. I think everyone can notice. So to avoid the damage of those portions, these SAR factors plays a challenging role, pivoting role, and for us, for the designers, it's very tough to design a biosensor, particularly on body or in body implanted biosensor, as because we have to strictly obey these SAR limit. We have to design that sensor within having SAR within that limit. It's a very challenging. Whenever we are increasing whenever we are decreasing the SAR to maintain that limit, we are decreasing the power also. Whenever we are decreasing the power, definitely the effectiveness of the device will decrease. So that there is a compromise. We have to do a compromise between maintaining this SAR and the power. So it's very challenging. So what I'm just telling you all, these are the personal challenges of an implantable antenna. I'm fast forwarding my slides just because I've already reached my limit. So first one, the miniaturization. Whenever we are placing an implantable device within implantable biosensor, whenever we are placing a biosensor within a body, it's implantable biosensor. Size is a great factor. We have to make as small as much possible. Think of an antenna. I have already developed an antenna which is 10 mm by 10 mm, thickness is 0.67. That means a flexible antenna. It will be placed at the pacemaker. So miniaturization is a crucial factor. Far field gain. Whenever we are placing an antenna we are placing not an antenna, rather than we are placing a biosensor within the body. The problem is that our body is very lossy in nature. So quite natural the signal which will be coming out of our body for the external world communication, the power of the device, the power of that not device, of that sensor will be very low. So gain is a crucial factor. We can't increase the gain. If we want to increase the gain, it will cross that SAR limit. Whenever we want to increase the gain, miniaturization can't be done, as because the dimension of the antenna, the radiating element or the radiating area, radiating aperture, it will get larger. So miniaturization, definitely there will be a compromise between the miniaturization and the gain. So definitely far field gain is a crucial factor whenever we are designing an implantable devices. This is the SAR issue. I have already mentioned restricted power and also the biocompatibility. We can't design any biosensor, particularly in-body biosensor, with any material. We need a biocompatible material over which the sensor has to be designed. And to be frank, very less biocompatible materials are available in India. That's why biosensors, particularly designing a in-body biosensor is very challenging in India. A 1 feet by 1 feet biocompatible material cost around 1 feet by 1 feet means 12 inches by 12 inches. Thickness is it can have any values 1.6, 0.6, 0.3, anything. It's up to you. It's up to your choice. So 1 feet by 1 feet biocompatible material will cost you around 9 to 10,000. See, if you have some research scholars who are doing they are designing biocompatible sensors, means in-body biosensors, quite natural funding is a great factor here. It's because the material itself is very expensive. So this is the implantable devices. I am giving you a broad insight about the medical devices, implantable medical devices, as because I'm working on it. And I would like to inspire some of you to do some research work in the medical electronics. So that's my main aim actually of this lecture. That's why I'm not going into any technical details rather than giving an overview. So this is the AICD. AICD is basically have some sensors like these implants. It will collect the data. There will be an external transmitter which has to be connected with your body externally, an external antenna. So the external transmitter will collect all the data from the implant and then it will transmit through this external antenna. This is the basic working principle of the AICD. It is no more in use after whenever the pacemaker and all such implantable devices arrived in the market. There is no more of use the AICD, but it is one of the primitive medical implanted devices. Now comes the pacemaker. We know what pacemaker do to a patient. Basically, whenever we have an abnormal heartbeat, the pacemaker detects that abnormal heartbeat and generates some electrical pulses to make that heartbeat normal. This is the basic working principle of a pacemaker, means a single line explanation of the working principle of a pacemaker. So nothing but it will generate the electrical pulses. The pacemaker has to be placed either in your abdomen or in your chest, 4 mm below the skin. It has to be placed. It can be a single lead, 2 lead, or 3 lead, depending on the problem in your heart. Single lead means these wires actually. The picture showing here it is of a 2 lead pacemaker, as because it has a 2 wire. That means the 2 wire has to be connected at either the right atrium and the left atrium, or the right ventricle or the left ventricle. That means it will generate electrical pulse in 2 electrical pulse simultaneously. If you have 2 problems, then you will have to use the 2 lead pacemaker actually. So my work on this pacemaker is a self-charging pacemaker. As we all know, I'm just fast forwarding again. So this thing has been developed my team actually. This is an antenna of 10 mm by 10 mm, 0.6 mm, and this is the matching circuit, and these are the microwave circuits. Actually, this device will generate, will not, rather than it has already been generated. It has already generated 900 millivolt from air. So the pacemaker, the battery of this black portion, almost 3/4 of this black portion of this pacemaker contains a battery, which is not rechargeable till now. So whenever a patient is using a pacemaker, that patient has to be get admitted at a regular interval of 5 to 7 years, the lifetime of that pacemaker. After again, a OT will be done, a new pacemaker has to be placed. That means replacing the old pacemaker, as because the battery will die. So the target of our team is to replace that battery with a rechargeable battery, and that battery will get charged from the air. So there will be no dedicated source for charging this battery. That's why we have termed it as a self-charging pacemaker. Of course, this is the future concept. We have just developed this segment. Now we are placing on that pacemaker to observe whether the battery of the pacemaker is getting charged or not. Definitely 900 millivolt is not sufficient to charge the pacemaker. We need a 5 volt. So we are using a DC-DC amplifier. What is the technical term of that? Self-driven voltage amplifier, DC-DC voltage amplifier. So no external energy source is required. No external power source is required for that amplifier also. It is just an IC from Texas, DC-DC converter.
So it is amplify this this 900 millivolt to 5 volt, so that the pacemaker can get charged. We are trying to develop that actually. It is in the research stage also, still in the research stage. So I'm just going. Bioelectronic eye. Pradipto, how much time can I have? That's because the lots of slides are here actually, particularly
Sir,
for the medical
you can
electronics.
continue 15
I
minutes
think you have an
more.
exam also.
Yes, sir. Yes, sir. 15 or 20 minutes, you can continue more.
So I can
Because
continue
we,
for more 10 minutes.
yes, sir. Yes, sir. 10 to 15
Okay,
minutes,
okay.
15
So
minutes.
this is a future concept. This is also a future concept, as because the Bionica is not in still in a commercial way. It is in the lab also. I have already shown you the first prototype developed by MIT. By the MIT. Actually, what's has been done in the Bionica, I'm just keeping all these languages. I'm just going into the. This is the first prototype picture. This is the actual thing actually. So what will be done? The patient has to wear a spectacles. Okay, there will be camera in front of the spectacle. The camera will capture the image. There will be a neurotransmitter at your retina. At your retina means, I think it is in my next slide. This portion. The retina actually is responsible for generating the image. As you can recall from our HS high secondary study materials, the rod cell and the cone cell, one is responsible for the color vision and other one is responsible for the black and white vision. Black and white colors, generating the black and white colors. And the rod cell and cone cell. These are the ganglion cells. So this is the retina. So now this information being collected by the eye will feed to the optical nerve. So if the retina is got damaged, so we will be using an electrode, neurotransmitter, just like this. So the camera will collect, this is the camera, will collect the data, will through the transmitter, he will send that information to the implanted receiver, neuro receiver at the retina. That neuro receiver will collect that data and will send that data to the optical nerve. So a blind patient, a blind person can see. But the problem is that the depth of the color will be barely 2 boot or 3D. Whatever we used to see in our natural eye, it is the 2 to the power 8, means 256 shades of a single color. If we talk about the RGB, red, green, and blue, there are 250 shades of individual color, red, green, and blue. But if we use the bionic eye, till now it is the 2B, 2 to the 4. That means the green will be of 4 different shades, or the red or the green. So the patient, that blind patient, can see the external one, but not the true color. It will say the patient can say that it is a green color, but it can't say it is a sea green or a different shades of green. Max to max 3 or 4 shades of green. That is the limitation till now of the bionic eye. But still, a patient, a blind person, or a blind person can see with this bionic eye. It's a hot topic. That prototype has already been developed. This one is the neuro receiver actually. The output of this neuro receiver will be connected to the optical nerve. The same concept is for the, I think it is a cochlear implant. And I'm very sorry that I haven't taken time now. So if the cochlea actually, this snail-shaped structure within our ear, inner ear, is responsible for generating the audio sound, which is being fed to the audio nerve. This is the audio nerve actually. So if it is being damaged, that means the person can't hear. So instead of a hearing aid, what we will do? We will put a transmitter along with microphone here. It will catch the external sound. Then through that transmitter, it will transmit the sound in a proper format, that is IOMT, that the medical data. Here the medical data will not transmit to the service provider rather than to the receiver with a proper protection. So this is a receiver, neuro receiver, which has to be placed near the cochlea. And then the receiver, the data received by this receiver will fed to the audio nerve. So that partially impaired hearing, the person who have a partial impaired, in case of hearing, it can improve the hearing, or it can overcome the hearing loss. So it is practically bypassing the damaged portion. Okay. So the neurotransmitter and the neuroreceiver practically bypassing the damaged portion. I want to show you some videos actually. That's why I'm just keeping these slides. There are lots of work are going on. It is the medical ingested device that the capsule endoscopy. My team are also working on it. So in case of endoscopy, I don't know whether you are aware of it or not. A camera with a small wire has to be inserted through your mouth. You will be LA. Either LA means local anesthesia or GA means. These are the medical terms actually. GA means the general anesthesia. That means you will be unconscious for a certain time. A camera with a wire has to be inserted through your mouth. It will pass through your entire digestive system, and that camera will take pictures and will send the data to the external device. That is the endoscope. But now capsule endoscopy has been entered in the market. You have to swallow a pill. I'm going to the pill directly. This is the pill cap. It has already been generated. You can see the size here also. So this capsule, artificial capsule, will rather than it has a optical light. It means a LED, a camera, battery to 2032 battery. 2032 is the name of the battery. Actually, size of the battery generally used in the computers. 2032 battery or 2016 battery. It will power the transmitter, and this is the board. The data, the camera, this capsule will pass through. It is a single-use capsule. After 6 hours, it will pass through your digestive system and it will pass out through the stool. It is a single-use capsule, and the Pilcan generally charges around 30,000 for this capsule only. It has been developed by in US actually. So this capsule generally works at 920 megahertz. The camera within the capsule will capture the picture. Then with the transmitter, through the transmitter, it will send the data to the external world. There will be a receiver at the external world, means nearest to the patient. There will be a receiver. That data will be collected by the receiver. Right now, what is happening? The patient has to wear a jacket. The jacket has a dash. Dash means the data acquisition system, and you have to swallow a capsule. The capsule will take the pictures, will transmit the data through your dash. After 6 hours, visit to your doctor and hand over the dash to the doctor. The doctor will have the entire picture of your digestive system, entire digestive system. So this is known as the capsule endoscopy. It is very costly now. It is presently it is working at the 900 megahertz, and I'm trying to make it at 2.45 gigahertz so that you can't have to wear that jacket. As because the 2.45 gigahertz is the Bluetooth frequency, as well as 5.2 gigahertz is also possible. So device will be much more smaller, as we all know that the frequency is inversely proportional to lambda, means the wavelength, and the device dimension is comparable to lambda. So whenever we are increasing the frequency, we are decreasing the lambda, means wavelength. That means we are decreasing the device size. So quite natural, the size of the capsule will be much more smaller. And the another aspect is the 2.45 gigahertz and 5.2 gigahertz is our Bluetooth frequency as the Wi-Fi frequency. So we do not need to wear the jacket. Rather than we can have an app in our mobile, and the data can be either through BLE, means Bluetooth low energy communication, or Wi-Fi. That data can be transmitted directly to your mobile. And if we use the IOM, that data can be directly transferred to your doctor mobile. So we do not need to visit the doctor again. That is that benefits of the IMT I have already discussed. We can't need to visit the medical practitioner in person anymore. So we are trying to develop this capsule at 2.45 gigahertz and 5.2 gigahertz. Of course, there are lots of complexity. That is, it is still in the research. We haven't the prototype yet. But this is the actual dimension which has already been in the market. SnowNet and the PILCAM, 23 mm and 25 mm. These are the two structures. Just showing you. This green one, number 8. These green ones, 7 and 8, is this board, this PCB. So I'm just keeping all those things. Wearable devices. This is an implantable devices. Okay, this that's bionic eye or the cochlear implant or the capsule endoscopy. Capsule endoscopy is the ingestible device. That means we have to swallow it. An implanted device is the bionic eye or the cochlear implant. We have to implant the sensor. Now, these are the practical examples of the wearable devices, means on body. I haven't taken much time, so smartwatch is one of the popular example. Wearable ECG monitor, it is already with us. We are doing some work. Wearable blood pressure monitor. So lots of research work can be done in these domains. So I just want to show you these research domains. So these are popular, rather not popular, rather than one of the hot topic in the brain-computer interfacing actually, BCI or BMI. My team is also working in this. And just BCI means in case of IOMT, there will be a communication between two medical devices, okay, through internet. In case of brain-computer interfacing, definitely there will be a IOMT role, IOMT, but in this case, the brain, the information will be collected from your brain. So the implant will be at your brain. It will collect the brain information. It will feed to the signal processing unit through IO management center. Then it will be the data will be processed and the steps will be taken accurately. That steps will be not taken by the medical practitioners in case of BCI. So IMT is present in the BCI or BMI. But the end, the third layer means that architecture. If you can recall that architecture, the third layer actually in case of IOMT belongs to the medical practitioners. But in case of BCI, it is an autonomous device. Depending on the signal processing, the signal being collected from your brain, depending on the signal processing, it will work. So the third layer will be changed in case of BCI. I'm just showing you. I'm showing on video. It has already been. These are the real-time works which are going on BCI in the different universities in our world. Actually, this research work is going on, is carried out by some PhD scholars in the Pittsburgh Rehab Neuroengineering Lab and the Blackrock Neurotech University, University of Pittsburgh actually, and the Neuroengineering Lab, the Rehab Neural Engineering Lab of the University of Pittsburgh are doing this work. I'm just showing him the video.
We started using the portable system
So this
in the
person actually,
lab a
this
few
person
years
have an
ago.
injury, so he can't move his hands. Okay, so by moving his just here, suppose I want to draw a picture or you want to type, so I will think it. The signal will be collected by the implant from the cortex of our brain, and it will fed to a digital processing unit, and automatically it will get typed. This is the basic concept of the video. Okay.
At first, we just used it to kind of do some cursor control and draw.
Check out signal quality.
In order to train a decoder, I watch the computer move a cursor to different targets. When it's moving to those targets, I just think about moving my own arm in those directions. It looks at the neural signals when I'm moving those directions and what I'm intending to do, and then I
Solitaire game of his brain by imagining moving his hand, imagining grasping his hand to click or unclick. So this was trained using a cursor task and recording from the neurons in his motor cortex. This can be used for a bunch of tasks like painting, and just many activities you might do on a computer.
having the ability to do that in some manner that is portable. It's not in a lab taking up a whole wall full of computers, and so I think that kind of thing could really change someone's life.
So it is an interdisciplinary subject, so anyone can. This is also an example of a woman who have a paralysis, and due to that paralysis, she lost her voice. So with a brain implant means and IoT and AI, they have generated a Alexa type model in a computer, and whatever the woman is thinking, instead of speaking, she is just moving her lips. The corresponding signal will be collected from the cortex of the brain through that brain implant, and through AI and speech processing, Alexa type model will speak it out. So practically the woman can have a voice, a paralyzed woman who have lost her voice. This is the woman.
Today is an opportunity for Anne and Bill to have a conversation through our brain decoding to facilitate what
a demonstration where we're decoding the two models yesterday, so we might need to test it a little bit.
Okay.
Because like
Yeah.
Yeah, we'll run
it
through
should
some
work.
This is an electrocorticography grid, which is attached to a pedestal, which is screwed onto the participant's skull. And it's the very first person to have this combination.
I think you are wonderful.
In the training lab, we really focus on restoring voice to people that have lost it due to conditions like stroke or ALS.
What we're picking up on are neural activity related directly to the attempts to move her facial muscles, and that's what we're able to decode into speech.
Hey Ann, how's it going?
It is good to see you.
Giving them the ability to communicate again with their loved ones and caregivers is really what we're looking to do.
I was thinking about running to the store.
What time will you be home?
In about an hour.
Do not make me laugh.
That's the first time we've ever had a conversation.
I have a little reflective sticker on them. It's very slow, and the device now is very old, but she relies on it.
For us to have that conversation using her Dynavox would probably be like a 5 to 7 minute conversation.
It was nice to have a conversation. I forget how slow this machine is.
When technology that can
Anything is possible.
Oh, you're showing not a lot.
Pet.
I guess we'll see. Are you?
Or write about pet.
With a group of students and fellows and engineers and scientists.
Again. This is another video on the.
When we first hooked everything up, for the first time of being able to move my hand, it was.
What is that? Here also, this guy has been paralyzed due to an injury, and he can't move his right hand. So what they are doing, they are collecting the signals from the cortex. The collected signal is being fed to the signal processor through communication channel, and then accordingly some sensors has been attached to his hand, which will activate the muscles. I haven't much time, otherwise I can explain the chemical reactions which are going, which whenever we are thinking something, we are speaking something, what works at our brain. It's nothing but a chemical reactions actually, which ultimately generates some electrical pulses. So whatever the sensor is collecting is nothing but some electrical pulses, some voltage changes, nothing else.
Big shock because before I had my injury.
So Ian had an accident. He was left.
The doctors told me that I had, and that most of
his injuries are intact, but the signals arrive at the injury in the spinal cord and they're completely blocked. He can't get to his muscles, so he can't actually do movements. So one of the things we've been working on is cells in the brain that are a tiny implant into the motor area of the brain, and we have this is kind of our window into Ian's. So now images of different types of hand movements, brain that are associated with signals.
So if I think what's kind of lighting up in me thinking about,
not only is patient relearning for several years, software is adapting and learning as well. And then that computer system is connected to another device that provides signals for the muscles in the forearm that drive hand and finger movements. Without the use of the system and the technology, Ian is not able to grasp objects. But once we connect the system and turn it on, Ian is actually able to open and close his hand. He is also able to pick up to a fine and he can pick up smaller objects. A paralyzed person has of development in the lab only, but we hope that one day we can take this technology to the point where it helps people not only with spinal cord injury, but also folks that have experienced a stroke or even a traumatic brain injury.
If all the work we're doing can help, so if you can give someone that.
And I'm very sorry that I couldn't be able to.
When we first.
So this is how the BCI works. I have already shown you the slides or the videos. Now what is going on at the back end, this is actually the slides. So I'm just fast forwarding it. Okay. Haven't any time. So the signal will be acquisited through the cortex of the brain, then signal processing, then the effector devices. These are the basic layers actually, basic architecture of a BCI. We already know the EEG. I have a EEG machine actually to collect the signals from the brain. And we have already developed a mind-controlled wheelchair with my graduate students, BTech students. If I think right forward, the car will move forward. If I think back, the car will move back. Up to these two controls, we have done it. We have done it in 2015. Those two guys are in US right now. They are doing PhD there through this EEG machine. So I'm just keeping out. There are different types of BCIs, how it works, where will be the position of the center. Lots of things are there actually. There are lots of BCIs also. It can be an invasive BCI, it can be a non-invasive BCI. I'm not going into the details. EEG is an example of a I am doing the non-invasive BCI actually. We couldn't be able to do the surgery to implant that sensor at your cortex. So we can't do it without the help of the medical practitioners. So we are doing with the EEG. Look, this is a BCI game actually. Without using your hands, just thinking by your thought process, that guy is playing a game, computer game. These are the ECG. These are the EEG sensors actually. This is a 10 lead EEG sensor. We have a 5-pin EEG, 5-lead EEG sensor. This is a 10-lead EEG sensor. It can capture 10
Sir,
different
your
brain signals.
audio is, you are not audible, sir.
I'm not audible. Just a minute.
No, sir, you are not audible.
But the mic is on. Hello. Am I audible now?
Yes, you are audible.
Yes, sir, you are audible.
Am I audible?
Yes.
Okay, actually my audio is being integrated with the camera. Whenever I switched off the camera, the audio goes down. It is thinking that the camera is off, the device is off. I'm sorry for that. So
Nothing
just
audible, sir.
I am not I'm not going through the slides anymore. So lots of things in a nutshell. I have lots of slides till now. It is a 54th slide. Till now I have a 30 slides. So demonstrating the recent research works which are going on the medical electronics actually, in which IOMT is a part only. So I'm not going through the slides. I think the slides is in sharing mode till now. So I am just going through the slides, nothing. These are the theoretical discussions actually, advantage or disadvantage, all the things. This is a microwave tomography. I am skipping this topic as because it is also a hot topic in the medical industry. Particularly, it is the medical imaging actually. We can't just in a nutshell actually. What is happening in medical tomography is that we can't scan the cancerous cell till now. We have to do the biopsy to determine the cancer. And it was my research topic in my PhD to do a scanning mechanism, to develop a scanning mechanism, to design a scanning mechanism which will scan the cancerous cell. So I have already developed the theoretical part in my research, in my PhD, during my PhD. Right now I am trying to develop in a practical also, so that the cancerous cell can be directly scanned. Actually, what happened, we can't scan a cancerous cell with the existing scanning mechanism, just like USG or X-ray or CT scan or MRI. CT means computed tomography. Tomography means imaging. So that's why the microwave tomography. My work was to develop imaging system using a 1 gigahertz signal, as because the 1 gigahertz signal is the only window through which the cancer cell can be scanned. It's a very limited, there is a crucial limitation here. We can't use any frequency. It's a theoretical study that only 1 gigahertz is the permissible frequency through which the cancerous cell can be scanned. So my research work was to develop scanning mechanism through by using this 1 gigahertz signal actually. So I'm skipping all these. Actually, these are my research works which I have done in my PhD. Lots of theory are there, lots of mathematics are there. So as a engineer, we used to neglect the mathematics in the first semester or second semester. But ultimately, whenever we are in the research field, we are in the research domain, that mathematics needs to be very, very clear. So during this research, again, I have to do all the mathematics classes in my in that institution actually. Again, I did all the mathematics classes just to have an idea of these. That's Scarborough. Scarborough means that iterative procedure, logarithms, algorithms, Newton-Raphson method, and that Leavenworth Markov method. So this was my model. That black one was the cancerous cells I have taken, and I have to reconstruct this image. So after 24 iterations, I got this image actually. This is my starting image. And this is the final image I got after 20 or 25 iterations. I have used I used during that time that Leavenworth method, and I did around 3,000, 4,000 line codings in MATLAB. The entire coding has been done in MATLAB. It was done in 2009, 2010. So this is my present work actually. But I haven't any time. Just in a nutshell, actually, I'm trying to measure the glucose level of a human body without any invasion. Means we do not need to prick, do not need to bring our blood out of our body to measure the glucose, which are the popular techniques right now. Just like this is a commercial glucometer. So what my team want to develop is just like a pulse oximeter. We have to clip on a device on your finger, and you have your glucose reading on the LCD display. So these are all the research works right now is going on, already been done. This sample one is my blood actually 107, and the reading came out as 110. Error is the 2.8%. This one is like just by placing. This is the clip actually. This one is the clip, and the result is this one. By clipping on 107 is the commercially available glucometer, glucose reading of my blood during that time. And 106.83 is the glucose level measured by my instrument. This is the instrument. This is a real time. I didn't make the clip enclosure. Right now, I am just placing the sensor in the ear. Later, there will be a 3D printing enclosure within which I have to put my index finger. So the reading is coming out of 106.83. That means the error is 0.158%. So these research are going on in the medical industry, not only along with my team. Several teams are working actually, along with the IMT as a part. RFNS, I am skipping the energy harvesting. It's a totally new domain. And I am skipping these videos also. It is actually the real-time application of telepathy. These videos, these 3 videos are actually, there are 3 videos here. These 3 videos actually deals with the telepathy. The telepathy is a practical thing. Lots of research are going on actually.
Mute and unmute your audio.
I'm just concluding my lecture. I don't know whether the lecture is interesting or not, but I have tried to convey you all the recent domains recent domains in the medical industry. It is not related to only to the electronics engineer. It is related to, it is an interdisciplinary subject. I need to know a lot about the biology, which we have studied in our HS. We have to discuss with our medical practitioners, our doctor friends. I am an electronics engineer with RF background. I need to discuss with my mechanical engineer friends, with my computer engineer friends to make a team so that we can at the end of the day. So it's our target. So I tried to convey you all in a brief the interesting areas of research, possibly interesting areas of research, I can say. So thank you all. I don't know whether you have got bored, you are getting bored or not. I'm sorry for that. You get bored, okay? So, Pradip, anything else? Hello? Hello? Can you hear me, Pradip? Can you hear me?
No, sir. You are not audible. Sir, can you mute and unmute?
Yeah, I did the unmute again. Am I here audible now?
No, sir.
No. I
Not
don't know what is
audible.
happening. Am I audible now?
No,
Yes, sir.
No.
Am I audible?
Not yet audible, sir.
I don't know. What
No,
is
sir, you are
happening.
audible.
Oh, audible. Okay.
Yes, yes.
Thank you for your patient hearing. I don't know whether you have got bored or not, but I tried to make the lecture more interesting without going into the details of the technology behind the IMT and all the medical electronics actually.
Okay, sir. Audible, sir.
So thank you all. Thank you.
Thank you, sir. Thank you for your very much informative session on IoT on medical things. And is there any questions regarding this topic? You are feel free to ask, sir. Please go on with participants.
I'm very sorry to cross my limit actually. Okay, 6:30 was
It's
my
okay,
limit.
sir. It's okay, sir. Please go on if there any questions from your participants.
Any question?
I think, sir, nobody has any questions. Sir, I want to ask you one thing that you have shown one capsule, wireless capsule. So
Yes.
when it will be in market?
Look, it is already in the market, but we have to purchase it from USA. Okay, it is already in the capsule endoscopy is already been in our Indian market, but that capsule has to be procured from USA. It has been manufactured by two companies. One is the Gen Glen and the Pilcap, and each capsule costs 30K for each capsule. Okay. Then after that, the doctor fees, as well as the admission fees, lots of will be involved in a single day. You have to admit in the hospital for a single day capsule endoscopy in case of capsule endoscopy. And my target is that capsule is working on 900 megahertz. Okay, that's why we have to wear a jacket, as because for 900 megahertz the communication length is 1.5 meter maximum. So we have to wear a jacket to keep that data acquisition system close to the system, close to the capsule. That's a drawback till now. So our research work, what we have, the outcome of our research work is that if we design the capsule at 2.45 gigahertz or at 5.2 gigahertz, by natural the capsule will get smaller in size.
Yes.
Rather than more important is that the communication will be of few of meters. Okay. So if I can have a mobile with me, and as because 2.45 gigahertz or the 5.25 gigahertz is the Bluetooth frequency or the Wi-Fi frequency. So it is readily available in the mobile. So we have to generate a mobile app to collect the data. The capsule will transmit the data in a similar way. Similar means similar to the existing technology. It will be just smaller in size. It will transmit the data either in 2.45 or in 5.2. So the data can be collected easily with your mobile if it is a near field communication. And if I can put that data through IOMT, that it can be sent to directly to the practitioner. So we can't have to visit the hospital to get admitted for a single day. So that's our target. We have designed the antenna. I have already seen that antenna, showing that antenna. We have designed that antenna. Now we are designing the circuitry actually. Actually, the problem is that in case of microwave, for designing antenna, you need to know the HFSS or HFSS or CST. But whenever you are going to design a microwave circuit, you need to know the ADS to design the passive components of the microwaves. So you have to acquire knowledge of lots of software to design those simulations, to run those simulations actually. These are, and those softwares are not included in our regular courses. So our students, both in BTech and MTech or in research, they don't know about anything about those softwares. That's a big problem. We have to teach them those softwares first, then we have to simulate that designs actually. So it takes a lots of time. So it is still in the research stage. We have designed the antenna, we have designed the circuits, we have designed the enclosure. We have studied all those things. Now it is under manufacturing process actually.
Okay, sir. Thank
Sir,
you.
for developing a micro.
Yes.
Please go on.
Sir, for the microwave imaging application for detecting cancer cell or scanning.
Yes.
So, minimum requirement.
Yes, pardon me. Can you repeat the question,
Whatever
please?
we need to design to scan for sir scanning cancer cells, different cancer cells. So, what
Yes.
kind of antenna we need to design and
Yes.
how we will integrate that antenna in a micro wave
Yes,
imaging application? I mean, any absorber required.
No observer is required here. I am just giving you an idea. Actually, I skipped those slides. I am just giving an idea. Just give me a moment. I'm just giving you the answer. I have already done it actually. So I can give you that answer right now, but the slide is not working right now. So just give me a moment. I'm just resharing the slides.
So, related question.
I'm just give me a moment. I'm just sharing a slide, the position of the antennas actually, which I have done in my PhD, during my PhD. Of course, that one is a theoretical study, but with a minimum error, I have got that orientation.
But in a practical, sir, in practical, it will interfere with another signal, na? So we need to design any absorber, or we need to test in a anechoic chamber only.
No, not in the anechoic chamber. Other than it can be done in the real-time environment. Means minus 10 dB noise in noisy environment. What we are doing, we are suppose. I can see you the. Actually, the slide has been stuck in a single position. It is not moving on. The slide. Windows 3.
Right?
We are using a microstrip antenna, patch antenna of 1 gigahertz, but of smaller size. And we can use the miniaturized also.
That we can do, sir. That we can do. But my question is whether it can detect all types of cancer cell or any specific cancer cell.
We are analyzing the scattering signal. Okay. Whenever the microwave, your biological body is being illuminated with a microwave signal, so instead of reflection, we will get the scattered signals. That's because it is an uneven surface. Now, what is happening? We are collecting. I have collected those scattered signals from all possible directions, means 360 degree, and then analyze those signals through my software to get an image of that cross section. That's the basic concept. Got it?
Okay. In place of measuring, we are measuring here scattered signal.
Yes. I am doing the scattering analysis instead of reflection or transmission. That's because the scattering is the common phenomenon of a microwave signal. So
Yes.
I don't know whether the slide is not getting. The slide is not getting shared actually.
So okay, I will go through your research article.
Power on. Bluetooth mode.
Thank you.
Device paired.
Okay, but you can collect my phone number from Prodipto so that we can communicate regarding this. Okay. I don't know what is happening.
Sure, sir. Sure.
Collect my phone number and give you all the details which I have done in my research work during my PhD. I can share my concept.
Yes, sir.
Okay. And I don't know what happened to my slides.
Okay.
Slides are not rolling on actually.
No problem. I'll go through with your literature and then I will get back.
Okay. Just contact with me. I will share you all my knowledge. What I know regarding this microwave tomography. Okay.
Okay, sir. Thank you.
Okay. Yep.
Thank you, sir, for your interactive session. And very informative it is. Sir, on behalf of our institution, I want to greet you with a small memento. Sir, please accept it.
Great.
This is
Nice.
for
Good
you.
design, nice. Thank
Yes.
you.
Sir, I'll send it later in your email ID.
Okay, no problem. Thank you. Thank you. Thank you.
Thank you, sir. Thank you for your session.
Sorry to not to be able to complete my lecture within the due time. Okay, I'm very sorry.
It's okay, sir. No problem. Thank you, sir. And
shall I leave now?
Yes, sir. Yes, sir.
Okay. Okay.
That's all.
Thank you all.
Okay. Thank you, sir. That's all for this ATAL FDP online program. This is the end of session 13, and now there will be a question answer session. We will go to the ATAL site and give the questions and give the feedback also about us, about each session. And please give the feedback in the meeting chat also, as well as the WhatsApp group which we have created. And also those are facing problem in giving question and giving a test. I'm checking it right now and get back to you very soon. If it is not possible to give this answer through ATAL portal, then we'll send you a Google form to give the answers. And there is a valedictory session from 7:30 to 8 p.m. Please be present there. Will be a photo session in unmute your camera mode, and that's all for today. Please check for the test.